Okay, so this is where we left it off, yesterday actually. So can you see the canvas, the blackboard?
Yes.
Yes.
Okay,
good. So what we were discussing yesterday is replacing D'Alembert's principle by an action principle. And so we saw that the action principle leads to the same Euler-Lagrange equations, okay? So now the idea is that we have to see what are the advantages to using this action principle, okay? And this is what we're going to be discussing now. So advantages to using the action principle. Let's capitalize this thing since it's something important. So by the action principle, I mean there is an action, which is the integral dt of the Lagrangian, okay, from T1 to T2. Okay, so let's see what are the things that we can learn just by thinking in these terms, okay? So the first thing that we can learn, which is a simple thing, but is very efficient, is that imagine that we have a Lagrangian. That we have a Lagrangian, which depends on some, generalized coordinates, q, q dot, and time, okay? And now we make a change of variables. So we just write q as a function of another set of generalized coordinates. So let me just be a little bit more precise, okay? So let me just write all the dependencies. So this is q of t, q dot of t, and then the explicit time dependence. And now we write, and we make a change of variables. So then q is a function of another variable s and t. And therefore, q dot is a function of s dot, and then also t. And this means that if I replace these variables q, q dot, and t by the new variables s dot, and t, then I'm going to have that the Lagrangian is a function of q, which is a function of s and t, q dot, which is a function of s dot, and t, and then also t. So this new function, the function which is the result of composing q with s, of making this change of variables, is of course going to be a different function. It's not going to be exactly the same function of s. So this is a new function of s dot, and t. And now the question is, what are the Euler-Lagrange equations for the new Lagrangian L prime? Okay, and one would say, well, I mean, all I have to do, since I know what are the Euler-Lagrange equations for L as a function of Q, all I have to do is make the change of variables and apply the chain rule. Well, that's an exercise, okay? So exercise, find this out using the chain rule. The standard chain rule for the derivatives, okay? But now we're going to do it in a different way. We're going to do it by thinking in terms of the action principle, and we're going to see that the answer is very simple. The answer to this thing is very simple, and it is the following. If, d dt dl dq dot minus dl dq equals 0, that's for all of them, okay, is the Euler-Lagrange equation for the old Lagrangian, for the old Lagrangian. Then for the new Lagrangian, the answer is identical. It's the same. It doesn't change. And how do we know this? How do we know that, after working out, the chain rule and taking derivatives and derivatives and derivatives, the answer is going to be this simple? Well, this is given by the action principle. What is the action of the system? Well, in the old variables is the integral from T1 to T2 of the Lagrangian, Q dot, and T. And now, let's forget about this thing. If somebody comes along and says, well, I have a Lagrangian L prime as function of the variables, the generalized coordinates SS dot and T, what is the action principle? Well, the action principle is the integral dt from T1 to T2 of the Lagrangian that you're given in terms of the variables that they tell you. And that's the answer. So it's as simple as this. There is nothing in the action principle that tells you that you have to use certain type of variables. So if you're given a Lagrangian in terms of some variables S, then you just write it down like this. And this is what the answer is. Okay? So you guys must have seen an example of this. Why by making a change of variables, actually the equations of motion do not change. I mean, in form, that's what I mean. They don't change in form. You still write down exactly the same order of Lagrange equations in terms of the new Lagrangian and the new variables. Example. So who can tell me an example of a situation like this that you guys have already encountered in the past? You guys already saw some of these things, right, in second year when you were doing classical mechanics, right? So there was something, you guys saw, Lagrangians, and you saw Hamiltonians. We will also see Hamiltonians here again. And so you already know about the Euler Lagrange equations. So who can tell me an example of a situation exactly like this? That, I make a change of variables and I don't bother about what is the new form of the Euler Lagrange equations because the form is the same. So, are you guys still there?
Yes.
Okay, so who can say something? Nobody has ever seen a situation like this before? Come on, I need some reaction. Let's see, who's here? So, for instance, I don't know, the first one on the list, Pau Colomer. What do you think?
Oh, I don't really know.
You don't really know, but you saw classical mechanics in second year, right?
Yeah.
And there was a Lagrangian.
Yeah.
Okay. So, for instance, tell me an example of a system for which you saw a Lagrangian.
C'è una baldufa.
Okay, so that's a spinning top. Okay, yes. Also, for instance, planetary motion, right? A particle of mass m moving on a plane, for instance, under a central potential. That's planetary motion. That's a simple one, right? You have a particle of mass m moving in a plane, under a central potential, a potential that we can think of like a 1 over r or something like this. Okay, so now you write down your Lagrangian. What are the coordinates that you choose? That was a question.
Still me. I don't know, spherical or cylindrical.
For instance, so you can choose spherical coordinates. If the motion is in a plane, I mean, spherical is fine, but polar coordinates is going to be simpler. So let's choose polar coordinates, for instance, okay? But you can always, okay, so polar coordinates is one possibility, but you can also choose Cartesian coordinates, right?
Mm-hmm.
And there is a change of variables from Cartesian to polar coordinates, right?
Yes.
Yeah, okay, so who tells you what are the coordinates that you have to choose? Why do you choose ones and not the others?
Well, depending on the system, it will be easier to solve one way or another.
Exactly, that's right. So that means that there is nothing that tells you that you have to choose one set of coordinates or the other set of coordinates, except the fact that you want your solution to be as simple as possible. But both sets of coordinates are perfectly fine.
Mm-hmm.
Do the Euler-Lagrange equations change whether you write your Lagrangian in terms of, Cartesian coordinates or in terms of polar coordinates?
No.
So that's exactly this.
Okay.
So that's exactly what I'm saying. You see, your Lagrangian L in terms of your variables Q could be Cartesian coordinates. These Euler-Lagrange equations have exactly the same form. You do exactly the same thing, whether you write your Lagrangian in Cartesian coordinates or in polar coordinates. So that's the statement I'm making here. So an example is the change of variables from Cartesian to polar coordinates. Oops. To polar coordinates. All right, so that's the thing. And this is immediately obvious if you think in terms of the action principle, okay, in the way I've been arguing here. Okay, so that's one advantage. Second advantage is that the action S integral dt of L from T1 to 2 encodes, encompasses, has all the symmetries of the system. So if the system has rotational symmetry, for instance, the action will know about this rotational symmetry. If the system has parity symmetry, then the action will also have parity symmetry. So the action knows about the symmetries of the system. And the symmetries of the system, we will soon know they are very closely related to conservation properties. So we will soon see through a very powerful theorem that is called Noether's theorem that whenever a system has a symmetry, there is a conserved quantity. So energy, momentum, angular momentum, all these quantities will be related to a symmetry. And the symmetry will be something encoded inside the action. So that's why the action is very important. Okay, so that's the second thing. Third thing is that the action, being the integral of the Lagrangian, is telling you that the Lagrangian is the important property. If you wish, the important quantity. If you wish, is the integral of the Lagrangian, actually, but the Lagrangian itself as well, since that's what you have to put here to integrate over. Okay, so that leads to an interesting question. Okay, which is quantum mechanics is based on the Hamiltonian. Right? I mean, all the courses that you guys have taken in quantum mechanics, they're always based on the Hamiltonian. The Hamiltonian is promoted to an operator, but you always play with the Hamiltonian. It's the Hamiltonian, and the Hamiltonian all the time. Okay. However, now we are saying that there is an equivalent formulation of theoretical mechanics that is based on the Lagrangian. So why is quantum mechanics not based on the Hamiltonian? I'm sorry, on the Lagrangian. Right? After all, you guys already know that theoretical mechanics can be formulated in terms of the Lagrangian or in terms of the Hamiltonian, and they are completely equivalent. There is no more information in one than there is in the other. It could be, for some problems, more convenient to use one formulation over the other, but there is no more information. What you can do with one, you can do with the other. So then how come that quantum mechanics, at least the way you have seen it so far, is not based on the Lagrangian? Have you guys ever wondered about this? Didn't you ask yourself why this is so?
Yes.
Because Hamiltonian has a direct relation with energy, and in quantum mechanics, and we want to know which is the energy of that state to have
Yes, in many cases, not always. In many cases, not always, the Hamiltonian is related to the energy of the system, but not always, not always. For instance, in particular, in the case of the electromagnetism, a particle moving in an electromagnetic field, we will see that the Hamiltonian and the energy are not the same. However, you guys use quantum mechanics to describe a particle in the presence of the electromagnetic field, right? So this is not enough. The fact that the Hamiltonian sometimes is related to the energy is not really the answer. The answer is that it is not true that quantum mechanics is not based on the Lagrangian. It's only the version of quantum mechanics that you guys have seen that is based on the Hamiltonian. So why is quantum mechanics not based on the Lagrangian? It is actually based on the Lagrangian, it is, but in a formulation which is called the path integral formulation. This formulation, I mean the path integral formulation, is totally equivalent to the, what should I call this thing? To the standard formulation of quantum mechanics based on the Hamiltonian that you guys have seen. This is actually a question that Richard Feynman, which was, because now he's dead, was a Nobel Prize winner, asked himself in the 1950s when he was doing his PhD. He was working on his thesis at Princeton, and he asked himself, based on a paragraph that he read you know, in Paul Dirac's book on quantum mechanics, he read a paragraph that led him to ask himself the following question: why is quantum mechanics not based on the Lagrangian instead of, you know, basing it on the Hamiltonian, as, you know, in the usual formulation? I call it usual because that's what, you know, most people see, right, in introductory courses to quantum mechanics. And so he started to think, what would be the way to really, you know, reformulate quantum mechanics in a totally equivalent way in terms of the Lagrangian? Okay, and then that's the way he, you know, got to the point of this, you know, path integral formulation. Now, I cannot explain this thing. I can only tell you what the answer is, and the answer is completely different looking. I mean, it looks different from the standard formulation in terms of a Hamiltonian as an operator and all this, but it's completely equivalent. And for some things, makes life, you know, life in quantum mechanics much more intuitive. So let me just say a few words about this thing so that at least you guys know that this thing exists, okay? What Feynman, you know, realized is that the important thing is the amplitude for a certain transition of a ket that is, you know, say located at the point Q at time t to a ket that is located at point Q prime at time p prime, t prime. So this probability amplitude, it will be the probability if I take the modulus square, is given by a very complicated and strange integral, which is the integral of I, that's the imaginary unit, divided by h bar, so this is quantum mechanical, and then is the integral dt of the Lagrangian from t1 to t2. So this object here is the action. So there you see how the Lagrangian is really playing the main role. And the integral here is an integral over all paths. So we have a situation in which we go from a certain point to a certain point, and we have to sum over all paths connecting these 2 points. So this is the point Q at time t, this is the point Q prime at time t prime, and we are summing over all Q's of t, going from one to the other. As we were doing when we were doing, you know, what is the stationary solution of the action principle. So it's the same set of paths. So therefore, they are infinite, of course. And quantum mechanically, I have to sum over all of them, okay? Over all of them, times this object here, I over h bar times the action. Okay. Just, you know, by looking at the expression, without really knowing how to compute it, you can already understand qualitatively several things. So for instance, recall the double slit experiment. What is the double slit experiment? The double slit experiment is an experiment that probably you guys saw the very first days of your course in quantum mechanics, in which you send, you know, some projectiles, could be electrons, could be photons, could be whatever you want, against the screen that has 2 little holes. And behind the screen, you see an interference pattern, right? You see an interference pattern. And then you have a hard time understanding how come that these projectiles, be that electrons or photons or whatever, actually go through 2 different paths to the same point. And that's the thing that forces, that provokes, that causes this interference pattern. So this is the interference. There's an interference pattern, right? And that is what quantum mechanics tells you. But you know, if you try to describe this thing, understand this thing in terms of a Hamiltonian as an operator that you have to diagonalize, this is not that easy to understand. However, in this formulation, this is obvious, because what this formulation tells you is that all the paths that connect these 2 points contribute. So you have to consider those that go through the upper slit and those who go through the lower slit, both of them. All the paths, these two, and also all the variants, right? Any other that goes like this or goes like that, and all of them. But immediately you see that, you know, you have to consider the paths that go through the upper hole and through the lower hole at the same time. But also we can now make a connection with, you know, classical physics, right? Because classical physics also talks about the action. That's what we have been doing these last 2 days, right? The action. So this immediately tells you what is the way in which you can obtain classical physics from quantum mechanics. What is the limit? What is the limit you have to take in quantum mechanics to recover classical physics? Have you thought about this? Since the answer, the world is quantum mechanical, but classical physics is a good approximation to that in a certain situation, right? There must be a way to take the limit from quantum mechanics and recover classical mechanics, right? What is this limit? Have you ever thought about this?
Yes.
So what is the limit, you know, to go from quantum mechanics to classical mechanics?
I would say that the width of the slit has to be similar to the de Broglie wave of the particle.
Something like that. Yes, it has to go with this, absolutely. But this is for this experiment, right? For the double slit experiment, for this experimental setup.
Or the action.
But how about in general?
The action related to the Planck constant.
Yes. What happens to the action?
If the action is similar to the Planck constant,
yes,
you have to use quantum mechanics.
Yes.
But if it is very large compared to the Planck constant, you can use classical mechanics.
Yes. How do you know this?
Quantum mechanics in class.
So somebody, in other words, somebody told you this.
Yeah, last day in quantum mechanics.
Okay. So let's try to understand this thing. Okay. Let's try to understand. Yeah, what you said is right. But let's try to not only remember this thing, but also understand it. Okay. Now, why is the size of the action relative to h bar the thing which is important to consider to decide whether we are in a quantum mechanics situation or in classical mechanics situation? Well, the first thing that you guys will remember is that what is the essential property of quantum mechanics? What happens in quantum mechanics for the quantities, for the physical quantities, that does not happen in classical mechanics for the same quantities? So we talk about momentum, we talk about energy, we talk about position, things like this.
They are quantized.
Yeah, they are quantized.
They are not continuous.
Yes.
And are probabilistic.
Yes.
The uncertainty. Heisenberg.
Yes. But what is the So if I take the position and the momentum, there is one essential property that takes place in quantum mechanics and does not take place in classical mechanics. In the relationship between these two.
Superposition.
Yeah, no, all that is true, but it's not the essential point.
Position and momentum does not commute.
Exactly. This is it. Exactly. This is the point. The point is that physical quantities in classical mechanics always commute among themselves, whereas quantum mechanically, the same quantities do not commute. Okay? This is the essential thing. And I mean, take x and p, okay? You know, the x coordinate and the p momentum, okay? They don't commute. So what is the commutator proportional to?
To h bar.
Exactly, h bar. So if we take the limit h bar goes to 0, then the quantum mechanical quantities would commute. Right?
Yeah.
So that means that whenever we can consider h bar as a small quantity, quantities will commute and we go from quantum mechanics to classical mechanics. So the limit h bar goes to 0, to make it in simple terms, the limit h bar goes to 0 is the limit in which quantum mechanics goes over to classical mechanics. And how do we see this in this fact in this formulation, this path integral formulation? Well, it's exactly what your classmate said, right? If h bar is small relative to s, or in other words, if s is very large relative to h bar, then we can always approximate this integral by the let me call it the minimum of s, or the stationary point of s, plus fluctuations around s at that point. So if we do this expansion of the action around this stationary point, then the fluctuations will have h bar in the denominator. But if the fluctuations are much larger, here we have an imaginary exponential. That means a trigonometric function. And those fluctuations will average to 0. So in the limit in which h bar is very small, or in other words, in the limit in which s, the action, is very large, all these paths are actually dominated by the path that makes the action stationary. That's the first term, because the fluctuations average to 0. But that's exactly what classical mechanics is saying. That yes, that the path that goes from qt to q prime t prime, in the limit in which h bar goes to 0, or in the limit in which the action is very large, or in the classical limit, is the path that actually makes the action stationary. So you see, this integral here, this path integral, is a very, very, very powerful connection, between quantum mechanics and classical mechanics. And it explains other things like this double slit experiment in a very intuitive way. Now, it is true that if you want to use this formulation to solve the hydrogen atom, you're going to suffer more than in the way they did it to you, in the quantum mechanical courses, okay, the quantum mechanics courses. So that's why, normally people do not talk about this, and they talk about, the standard formulation based on the Hamiltonian. But this formulation is very powerful. And actually, I must tell you that all the fundamental theories of today that describe all the fundamental interactions of nature are based on formulations like this. They are completely equivalent to Hamiltonian formulation, but they are more powerful. And there is an extra advantage to this, which is that we will soon see that the action can be made relativistically invariant, and nature is relativistic, whereas the Hamiltonian cannot be made relativistically invariant because it singles out time, right? The energy is not relativistically symmetric object. Okay, so this was, you know, a parenthesis having to do with why, you know, the Lagrangian and the action principle is actually much more interesting than just, you know, what it does in classical mechanics. It has very strong connections and implications in quantum mechanics and you know, in the formulation of the fundamental theories that we know today. So that was point 3. Okay. Now, any question before I move on to point 4? Any question?
No.
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 Okay. 4. The action principle immediately tells you something that otherwise is not that simple to realize of, which is that the Lagrangian is not unique. That you can have the same Euler Lagrange equations with different Lagrangians. For instance, you can have a Lagrangian L with these Euler Lagrange equations, and you could have the same equation. So let me just say the same. The same equations for another Lagrangian L prime. And now the question is, what is the relationship between L prime and L? Right? The coordinates are the same. So they are still Q. I'm not making a change of variables. The only thing that I'm saying is that if it is true that these equations are the same as those, what is the relationship between L and L prime? And there is one which is completely trivial. So can you guess? Can you guess what is the relation between L and L prime that will make this statement true? How can I change the Lagrangian without changing anything?
Multiplying by some constant.
Exactly. Very good. Absolutely. So if I multiply this by a constant, I'm changing nothing. The solutions to the equations of motion are going to be exactly the same. So I can always take a Lagrangian and multiply it by any number I want. Another one.
You can also add a constant.
Aha, very nice. So I can add something here. I can add, what you say is true, I can add a constant. Why? Because whenever I take derivatives, the constant drops out. So, I mean, adding any constant I want to the Lagrangian, again, does nothing to the equations of motion. So it still describes exactly the same system. But it is a constant, the most general thing that I can add to a Lagrangian without changing the equations of motion.
It can depend on
time.
You're going to have to repeat because the sound was very bad.
You can
There is some
time.
reverberation. So let me tell you. The answer is that you can add to the Lagrangian any function of the coordinates, the generalized coordinates q and the time t, if you take the total derivative with respect to time. Any function that you add here will contribute nothing to the equations of motion. So exercise. verify that d dt derivative with respect to q dot, derivative with respect to q, this operator acting on the total derivative of f with respect to t, which is a function of q of t and t, give you identically 0. So using L prime or using L is going to give you exactly the same equations of motion. Now, this exercise is an interesting exercise in the chain rule. So if you do it and you get to verify this thing, it'll show that you really know what depends on what. So that Q depends on T, you know, what is the dependence on Q dot and stuff like this. So do the exercise because it's very interesting. But now we're going to show this basing our arguments on the action principle. Okay? So what I'm saying is that let's take L prime now and we write S prime as an integral over T from T1 to T2 of L prime. And the statement that I'm making that the physics doesn't change by adding this derivative of f is the statement that I'm going to get exactly the same solutions from the stationary principle for S prime as for S. Okay, so this is A times the integral dt from T1 to T2 of L plus the integral dt from T1 to T2 of the total derivative with respect to time of f. All right? Now, what is the first term? Well, the first term is clearly A times S, the action that I had when I was dealing with L only, right? Plus, what is the integral over time of the total derivative of f with respect to time from T1 to T2? So, now, math. What is the answer? I have the integral of a derivative. So what is the answer to this integral?
It's the function f evaluated in T2 minus
f of q times T2
minus f evaluated on T1.
f q of T1. Okay? So that's what I'm adding. I'm adding this difference of the function f, right? So now, the stationary principle. Says, make the variation of S prime and equate that to 0. Okay? That's what it says. You're going to get the right Euler-Lagrange equations from this condition. So this is A times the variation of S plus the variation of this difference, Q of T2 minus F Q of T1. Now, what is the variation of this difference? Can anyone tell me?
I think it has to be 0.
It has to be 0 because otherwise what I'm saying is not true. But why is it 0?
Because the points are fixed. The endpoint.
No, not exactly. Not exactly because the points are fixed, because I'm not taking a variation with respect to T2. Remember, this variation is respect to the paths that connect 2 points, right? The point, say, T1, Q1 with the point T2, Q2. Right? It was the path connecting this. So what is the reason why this thing is 0? Remember, we are taking variations, so doing variations of the path, right? That's what we are doing in the action principle, to look for the stationary point. We are looking for the stationary point, making variations of the path that connects these 2 points. Okay? Do we agree or not?
Yeah.
Yeah.
So why is this 0?
Because things of the past has not changed. If you make a
I cannot understand what you're saying. Can you repeat, please?
if you make a variation on the path, the extreme points does not change.
They don't change. Exactly. That's the thing. Exactly. So this is 0. This is 0 because delta Q1, 2, I'm sorry, delta Q T1, 2 is 0. They don't change. There is no variation here or here, right? There is no variation. I mean, this variation here is going to be the derivative of f with respect to q delta q at t2. But delta q at t2 is 0. And this is going to be the derivative of f with respect to q delta q at t1. But delta q at t1 is also 0. So therefore, the two separately are 0. Okay? So that's why this derivative of f does not contribute. And therefore, the equations of motion are going to be exactly the same. So you see how clear this is. It's very simple. You don't have to do all this chain rule differentiation. So if you do the exercise, you will appreciate more, the powerfulness of the statement, why this thing is simple. And then, of course, the solution is given by this, which is going to be the same, right? Because a is a constant, and I can divide it out. I can divide by a. Okay? So this means, let me emphasize it again, that I can always add to a Lagrangian a total derivative of a function which depends on q. Could I have this function depend on q and q dot? Here is at q and t. Can I add a q dot there or not? So generalized velocity. Can I say, well, there is a possibility that f could also depend on the generalized coordinate and the generalized velocity q dot. Can I put a q dot in there? Yes or no?
No.
No.
No, not why?
Because we have.
Because q dot is not fixed in the extremes.
Exactly. Very good. Precisely. If you go back, several slides, let me see how many. Look at this, right? Look at this condition. Well, look at this condition, if I can get the red color. Yes. There is no condition on eta dot, right? No condition on eta dot. So that means that there is no condition on delta q dot, no condition on the generalized velocities. And therefore, I cannot put in this f a q dot, because then this would not be true with a dot. It's only true without a dot. All right? Okay, so enough about the action principle. Any questions so far, or comments, or whatever? No questions?
No.
No.
Okay. So now we're going to do a little exercise, which is going to be an extension of Hamilton's principle. So that's to say, an extension of the Euler-Lagrange equations of motion for systems which are non-holonomic. So let us remember what non-holonomic systems were. Extension to non-holonomic systems. So these systems are more complicated than the holonomic ones. So what were the holonomic systems? The holonomic systems, non-holonomic. The holonomic systems were those in which the constraints did not depend on velocities. Remember? The constraints, were just, some functional relationship between, the coordinates. Some condition that did not involve the velocities. Non-holonomic are those that do involve velocities. The constraints involve velocities. And therefore, you cannot solve the constraints to write, the Cartesian coordinates, for instance, in terms of the generalized coordinates. That was the initial point. How did we define generalized coordinates? Those were the ones that were independent, that solved the constraint, and those were the ones that we could write the initial Cartesian coordinates in terms of them, right? In a non-holonomic system, since there are velocities, we cannot do this. Okay, and then what do? If we cannot, right, we cannot write Ri in terms of Q, J, and T. This we cannot do because there are constraints, okay? There can be a constraint that now is going to involve velocities, right? Velocities. Then what do? Well, we're going to discuss this situation is more complicated, and so we're going to simplify. Let's concentrate on a simplified case. And the simplified case is going to be constraints of a certain form. So they will involve velocities, but in a certain specific way. Okay, so it's going to be some function of the q's and time times q dot. So that's the dependence on velocity. It is linear, plus another function that I'm going to call a sub 0, which is another function of q and t equals 0. So that's a constraint. It involves the velocities, okay, and is a constraint. And this can be for all the variables, right? So I can put here an index k, and here I have an index k, okay, and that would be one constraint, okay. This is a sum over k from 1 to n. So imagine that I have a constraint like this. It is a constraint that involves the velocities. But I can have more than one constraint, right? I could have more than one constraint. I could have one of these conditions, or I could have 25 of these conditions. So this is going to be another index L that I'm going to put here. And L is going to go from 1 to m. And m is going to be smaller than n. So my Q case, K goes from 1 to n, and I have L constraints. like this. I have L constraints. What I mean is, that I have L equals 1 to M constraints, like this. Okay, so now I have a constraint, actually M constraints, involving the velocities q dot. Okay, what do I do about that? I don't like this notation here. I'm going to change this 0, and I'm just going to put it a hat. Actually, this second function here is going to become irrelevant in a minute. Okay, so that's why, you know, I can change the name. Okay, but it's clear that I have one of these equations for each index L, and L goes from 1 to M. So I need to have less conditions than variables, right? Otherwise, the system is going to be over-constrained, and there might be no solution. Okay, so I have these constraints, this set of constraints. Then the first thing that we are going to do is we're going to see what these constraints have to say for the virtual displacements. So what do these constraints imply for the virtual displacements? This is the crucial question we have to answer, as you will see. Well, let us write each and every one of these constraints in a different way. So I can write it as sum from k equals 1 up to n. I have a, l, k, q, t. And now I can write dq, k plus a hat. Well, actually, you can do it like this. Well, that's okay. I can still do it. A hat L of q t dt equals 0. Right? You agree with me that this equation that I just wrote down is exactly the same as the constraint that I have up here. Do we agree?
Yes.
Okay, good. So this is a real displacement. How do I know that is a real displacement? Because time has changed. Okay, that's you know, the definition of a real displacement is how things move when I let time evolve, when I let time change. How do I identify a virtual displacement? If I do the same thing, but I freeze time, so I put a 0 here. If I do the same thing by, you know, killing delta t, then this is going to be the condition for a virtual displacement. So these constraints impose on the virtual displacements these conditions. These are the conditions which are important in what follows. So the constraints, these constraints impose on the virtual displacements these conditions here. Then what? Well, then what we have, so let's go back. What we have is that if we did not have these constraints on the virtual displacement, then we would know what to do, right? Without these constraints on the delta qk, we know that the answer is given by the stationary condition on the action S. right? So S will be given by the integral over T from T1 to T2 of the Lagrangian, Q dot, and T. Then, without the constraints, the solution is given by this stationarity principle, ds equals 0. And this leads to, d dt. I'm going to write it starting from the other side. This is completely material, but let me just do it like this. This is going to be dl dqk minus d dt dl dq dot k times delta qk integral dt from t1 to t2. And this I have to sum over k. Sum over k from k equals 1 up to n equals 0. This is what the action principle, the stationarity of the of the action, would give me. It yields exactly this condition with a sum over all the coordinates. Now, without the constraints, without these constraints, how did we argue? That from here we can get the Euler-Lagrange equations, for each qk. Because we were saying delta q's, these delta q's are independent. That's what we said. At this point we said, when we didn't have any constraints, we said the delta q's are independent. So therefore, each and every one of the summands here has to vanish. Okay? But now, that had changed. Now, the delta qk's are no longer independent. But they are linked, connected by the constraints. Which constraints? Well, the ones that we had before. This equation right here, okay, which I'm going to write down again. So by the constraints, sum from k equals 1 up to n, ALK of QT, delta QK equals 0. So those are the constraints, right? Look at this, exactly this. So now we have a situation in which, now we can only say that, well, we can still apply, the lemma of the calculus of variations, okay? So it is still true that from here we can conclude that from k equals 1 up to n of derivative of L with respect to qk minus derivative with respect to time, derivative of L with respect to q dot k delta qk, this has to be 0. But the delta qk's, this is like this, delta qk. But the delta qk's are no longer independent. If there were no constraints, the delta qk's would be independent, and therefore each and every one of these terms would give you 0, would have to give you 0. And then we would have, n equations for each and every one of the qk's. But now the delta qk's are no longer independent. They are fixed by these conditions. How do we go about solving this thing? What can we do? We have this, but we also have to satisfy that. What can we do about this? Can anyone guess? I mean, one way would be, well, out of all these conditions, let us see which are the delta qk's which are free and which are the delta qk's which depend on these delta qk's which are free. In other words, let us solve this, constraint and then replace the constraint inside this equation. Now, that would be one way to go. But this is very complicated, and in this is very, cumbersome. It's difficult to carry out this thing unless, I know exactly what constraints I have and all this. But there is a method that allows me to solve this type of problems, right? Now I have this condition, but with a constraint. And this condition is a condition on the stationarity of something, which, well, let me just say it, okay? Is a condition, is a extremum condition, is a condition on the extremum of the action. So I have this with that constraint. What can I do to solve this?
Lagrange multipliers method.
Exactly. Very good. Exactly. The Lagrange multipliers method tell me that if I add to this equation lambda times each and every one of the constraints with 1 lambda for each constraint, so that means I add here a sum over L from 1 to M because I had M constraints, right? Lambda L times sum from k equals 1 up to n, ALK, QT, delta QK. Then the delta QKs become independent. They become independent. That's the miracle of the Lagrange multiplier method. Once you add a Lagrange multiplier times the constraint, then the differentials, these differentials here and here, become independent. And therefore, you know, what we find is that dl dqk minus d dt dl dq dot k minus the sum over L from 1 to n lambda L ALK, this has to be 0. This is the solution. And these guys are Lagrange multipliers. Lagrange multipliers. Okay, questions? Why do I have a minus sign? I made a mistake. This is a plus. I mean, the sign could be plus or minus. Remember that the Lagrange multipliers, you know, you could add them or subtract them. Doesn't make any difference. But if I put a plus here, I have to put a plus here. Questions? So this looks like a miracle, but you have to go back and refresh yourself, you know, of what the Lagrange multiplier method is about, okay? And you will see that this is true. And actually, you know, let me just show you that many days ago at the beginning, we argued about this. Let's see if I can go back enough pages. When we were talking about virtual displacements and the method of Lagrange multipliers. Let us see. At some point, I think I was talking about this. No, I'm sorry. It's not in these notes. It was the very first day, and so therefore is in the notes that you guys have in the Campus Virtual in LaTeX. Okay, because the very first day I could not record the class. Okay, so it's not here in these written notes. It's in the notes in the LaTeX version. So I cannot show you right now. But if you go there, you will see that the method of Lagrange multipliers does this thing, does this trick, you know. It transforms the differentials from dependent into, you know, independent, just by adding lambda times the constraint. So now we can give, to these Lagrange multipliers, to this term here, and a certain interpretation. So let me write down this equation in a slightly different way. So I'm now going to write it as d dt partial of L with respect to Q dot K. So now I write this term first, minus dL dQk. And this equals, let me just make sure that I don't make a mistake. This is the sum from L equals 1 up to M of lambda L ALK. So I just pulled to the right-hand side the term that comes from the Lagrange multipliers, okay? Now, so these are now the equations that I have to solve. Yeah? So this is an A, yeah? This is not a Q, this is an A. ALK. Okay, this is for K from 1 up to N. Is an equation for each generalized coordinate, QK. And to this condition, we always have to add the constraints. This is also what comes with the Lagrange multiplier method, right? I mean, you have a condition on the derivatives, but there is also the constraint. So the constraint is the sum from K equals 1 up to N of ALK QK T Q dot K. That was the original constraint. Huh? That's the original constraint. That's what I have to add. 0. And this is for L from 1 up to N. Okay? That is the original constraint before I started to see how the constraints affect the virtual displacement. I started with this constraint. So these are the equations. To solve. I'm sorry, to solve. Okay, now, the last thing that I want to say today is that written in this form, now we can give an interpretation to the term sum from L equals 1 up to M lambda L ALK. So the term that comes from the Lagrange multipliers. Who can tell me what kind of interpretation can we give to a term that is sitting on the right-hand side of the other Lagrange equations?
Generalized forces that not depend on a potential.
Absolutely. Very good. Yes. So generalized forces. We're going to have one generalized force, or at least one generalized component, for each of the generalized coordinates. So QK, yes, can be given this interpretation. So those are the generalized forces. As we saw, when there were generalized forces that could not derive from a Lagrangian, generalized forces. And that is for K from 1 up to N, one for each of the generalized coordinates. So that means that, we can reinterpret this term written in terms of the Lagrange multipliers as the generalized forces responsible for what? What can be the role played by these generalized forces? What do they do to the system? The system without the generalized forces would be the system without the constraints. We had to put these Lagrange multipliers because there were these differential constraints, right? In terms of the velocities. Without the Lagrange multipliers, the system would be without these differential constraints. So what do these generalized forces do for us? What are they responsible for?
for these constraints.
Exactly. They are responsible for the differential constraints. So we can find now which are the forces which are responsible for the constraints. And this can sometimes can be, beneficial, can be advantageous, because most of the times we do not care about the forces which are responsible for the constraints. Remember, let's go back at the very beginning. At the beginning of the course, we said, given the constraints, we need to know all the forces which are responsible for these constraints in order to solve the equations as Newton would solve them. But this is complicated because we don't know which are the forces responsible for the constraints. So we get rid of these forces by applying virtual displacements and then going to the Lagrangian and the other Lagrange equations and blah, blah, blah. But there are situations in which maybe we want to know what the forces responsible for the constraints are. So that will be a way to obtain them from this formalism of the stationary principle and Lagrangians. And we're going to see an example in which we will see, how these generalized forces are obtained in a specific case. So that, and we're going to see how, these forces, can be obtained with the formalism of Lagrangians and generalized coordinates and all this. So if you work enough, you can always find everything in one formalism or in another. But that will be tomorrow, okay? So right now it's already 2 hours. You guys are tired, and 2 hours, looking at the screen, it's already a little bit tiresome, okay? So I'm going to stop at this point.